Hello friends, welcome to EK Lectures. In this lecture, we are discussing the distributions from statistical mechanics. We will be discussing about Maxwell-Boltzmann, Fermi-Dirac and Bose-Einstein distributions. Distributions. Distributions arise due to different types of particles. We have different distributions for different types of particles. So depending on the type of particle, we have either Maxwell-Boltzmann, Fermi-Dirac or Bose-Einstein distributions. Now any identical particle can be classified into either classical particle or quantum particle. Now classical particle have the property that they are distinguishable. You can distinguish from one another, distinguishable. Now the term distinguishable means if there are two particles A and B, if R is the average separation, expectation R is the average separation, if it is greater than the wavelength, de Broglie wavelength associated with their motion, then this particle is considered to be distinguishable. Okay, now if a classical particle distinguishable particle obeys Maxwell-Boltzmann statistics. Boltzmann statistics, and we have to remember that generally we consider the ideal gas, and ideal gas is not a distinguishable particle. Or the particles of ideal gas is not a distinguishable system. Okay, now coming to the quantum system or quantum particles, they are also identical particles, but they are indistinguishable. You cannot distinguish from one particle to the other. So indistinguishable particles. So these indistinguishable particles are classified as either fermions or bosons. Fermions are spin half particle or 3/2 particles, uh, while boson is integral spin particle with the spin 1. Integral spin particles. Now these fermions obey Fermi-Dirac statistics, while the bosons obey Bose-Einstein statistics. Okay. Now is this here ideal gas? We also have a Gibbs factor. Gibbs factor, which is equal to 1 by n factorial, where n is the total number of particles. Now since it is an indistinguishable particle, the average separation is very much less than the lambda. In Maxwell-Boltzmann distribution, there is no restriction on number of particles in a state. No restriction on number of particles in a state. Which means you consider a particle A and particle B, these both can stay together in a single state. And Also you can have more number of particles in a state, that is given by A, B, C, D, where A, B, C, D are different particles, very different identical particles. Okay, distinguishable, this is important. Distinguishable but identical. Now another property is the if we exchange the particle, between the states or energy level, we get a valid state. For example, these are two states. Particle A is in a ground state, particle B is in a first excited state. If you exchange, the levels remain same, but here particle B will be here, particle A is here. Now these both are valid states. Okay. So these are the properties of Maxwell-Boltzmann distribution. There is no restriction on number of particle. They can stay, any number of particles can stay in a particular state. Also, if we exchange the particle, you get a different state. This first state here, this is called in first state A, comma second B. Here first state B, second state A. So this is a two distinguishable states or a valid state. This is both case 1 and 2. Let us take this case as 1 and 2. Both cases are different. That is what is meant by having a valid state even after exchange. Fermi-Dirac distribution, the distribution number 2, and here the conditions are: the state contains either single particle or no particle. If this is the system, either it has to contain one particle or it should be left blank. Only these two conditions are possible. You cannot have the same state with this is 0, this is 1, and you cannot have this particular situation. No two states or no two particles can occupy the same state. That means this includes accounts for the spin. Okay, so the particles are same kind. So this is how the particles will be in a state or fermions. We are talking about fermions whose spin is equal to half, whose spin is half. Okay, so half or 3/2, half integral spins. So the spin is half, means it cannot have the same state, cannot have, or the particle cannot have different more than one in one state. Okay, even when they say that one has to be spin up and another has to be spin down, they are both in different states. They are not in the same state. Okay, now the continuation of the first is they obey Pauli's exclusion principle. Pauli's exclusion principle. Now, what is that? No two spin half particle can occupy, or no two particles can have all the spin, all the quantum numbers the same. Okay, no two particles can have all the quantum numbers same. Okay, now for spin half, which is given by S is equal to half, the degeneracy possible is, degeneracy means the energies, levels having same energy. Degeneracy is 2s plus 1, that is equal to 2 into half plus 1, that's 2, 1 by 2 plus 2. Yeah, all right. Now if it is spin 3 by 2, degeneracy will be equal to 2 into 3 by 2, 3, that is plus 1, that is 4. So 4 particles can present. So 4 particle is present in this way, not in this way. Okay, this is not the case what they are talking about. Degeneracy. Degeneracy means energy levels with same energy. Interchange is not possible. You cannot interchange particles. If you interchange the particle, you get a different state. Interchange is not possible, as well as togetherness. The particle cannot be together. It is also not possible. The degenerate state, or degeneracy means the state with they are all different states but with same energy. They have the same energy. That is the meaning of degeneracy. Bose-Einstein distribution. So in Bose-Einstein distribution we have all the particles are similar. You cannot distinguish between the particles. Okay, yeah, and the things are no restrictions on number of particles. Okay, any number of particles can be accumulated in a state. Now next thing, interchange. Interchange is possible or not. Now to understand this, let us consider that there are two states and two particles. First particle is in first state and the second particle is in second state. Now I am interchanging this. Let this particle go to the first state and the particle in state 1 go to the second state. So A will come here, this will be coming. So here the first state, this is the second state. So from this is the first state and this is the second state. Is there any change? There is no change. So since there is no change, both are the same state. So interchange not possible. That means if it has to be possible, the interchange after interchanging we should get a new state, but because here we are getting the same state because the particles are identical. So this is due to identical particles. Now coming to togetherness, yes, we have already defined that any number of particles can stay together. So A, this is state 1. So any number of particle can be stay together. So this is togetherness is possible. Here we have a question that is, in Maxwell-Boltzmann distribution, we have to distribute two particles in three different states. So since we are dealing with Maxwell-Boltzmann distribution, we have the conditions such as so let us discuss what is the type of the particle. Type of the particle is identical. They are identical particles, and apart from being identical, they are also distinguishable. So identical and distinguishable. So what are the particles, or what can be the particles? A comma B. Right, so two particles A and B. Now what were the conditions? Interchange is possible as well as togetherness. The particle can be together. The interchange is possible because the particle has particle is distinguishable. Okay, so now here we have three different states, 1, 2 and 3, and we need to find how many different possible states are there for two particles in three different states. Okay, yeah, basically we are going to find out how many different energy levels energies are there here. So particle A here and particle B. Since interchange is possible, we can write A and B. So this is the first state. Second, now I am placing the particle A here and B over here. So here this is the third state. Now interchange A here and B. So this is another state, state 4. Now what can we do? We can raise the place the particle over here, A and B, and interchange now A, B. So it becomes 4th, 5th and 6th, 5th, 6th state. Now what we can do? You can have particle can stay together. That means A and B can stay together in the first state. Sorry, A and B. So A and B in the first state, that means you have the 7th state. The A and B particle can be in same state, where that is in 2, that is it will become the 8th state, and AB 9. Now look at this, 9 different states are possible with 2 particles in 3 different states. So this is Maxwell-Boltzmann. Those are classical particles. Fine. Number of ways of arrangement or number of ways. Okay, number of ways of arrangement is equal to the number of states into number of states whole to the power number of particles. So for classical systems or classical particles, obeying Maxwell-Boltzmann distribution, you can write the number of ways of arrangement is number of states to the power number of particles, that is 3 to the power 2, which is equal to 9. So we have 9 different states or 9 different ways of arrangement. Here we have two systems with Fermi-Dirac and Bose-Einstein. The same question, we have two particle and three states. How can we arrange? So this is Fermi-Dirac. Interchange is not possible in Fermi-Dirac because the interchange will yield to same state because of the particles are indistinguishable. Here both the Fermi-Dirac and Bose-Einstein are dealing with the particle which are indistinguishable. That means both the particles are A and A, same and similar. You cannot distinguish between them. So the states 1, 2 and 3 for Fermi-Dirac, interchange is also not possible, togetherness is also not possible because they obey Pauli's exclusion principle. So if I place the particle A here, the next particle has to be here. It cannot be on the same cell. Okay, that makes my first combination. Now the second one, if I have to place the particle over here, second particle has to be here because this is already done. Now third one, second and third. So only these combination, only three combinations are possible in a Fermi-Dirac system with the two particle in three system or three states. So number of ways of arrangement. Arrangement is given by 3C2, which is number of states C particles. Okay, so states C particle, combination is states C particle. 3C2 is 3 factorial by 2 factorial into 1 factorial. For Bose-Einstein statistics, the particles are not interchangeable because the particles are indistinguishable. Now togetherness is possible because they do not obey Pauli's exclusion principle, or you can write spinless. Okay. Now two particles, the particles are both A and A because it is indistinguishable. Both are similar particles. So arranging them in three different states, the first possible way is A here and A, next one A. Now since togetherness is possible, both the particles can stay together. Two particles stay together in first state, two particles stay together in second state, or two particles stay together in third state. So it gives us 1, 2, 3, 4, 5 and 6. So 6 possible ways of arrangement are there for Bose-Einstein particles or bosons. Now through this session we will understand how to find the partition function of a certain distribution, which includes the Maxwell-Boltzmann distribution, Fermi-Dirac distribution, and Bose-Einstein distribution. Now let us first see about the Maxwell-Boltzmann distribution. In a Maxwell-Boltzmann distribution, suppose if there are three energy levels and one particle. So one particle in three energy levels. So this is E1, E2, E3. We assume that there is only one particle right now. So one particle can be in any of this state. So partition function Z for one particle is equal to sum over S. S represent the number of states. The sum over S e to the power minus beta Es if there is no degeneracy. If there is degeneracy, we will use sum over S Gs e to the power minus beta Es. In this case, for one particle system, we have Z1 sum over S is equal to 1 to 3 e to the power minus beta Es. So Es is E1, E2, E3. So this gives us e to the power minus beta into E1 plus e to the power minus beta into E2 plus e to the power minus beta into E3. So this is the Z1 partition function for one particle. Now the particle need not be always one. For n particle system, we have Zn, which is given by Z1 to the power n. Okay, so this is for if the particles are distinguishable particles. Maxwell-Boltzmann are distinguishable. For this is for distinguishable particles. Now for if the particles are indistinguishable, now if the particles are indistinguishable, one example we have seen, the example of the ideal gas. Ideal gas, though it belongs to Maxwell-Boltzmann statistics, they are indistinguishable. Particles of ideal gas molecules are indistinguishable. So then Zn is equal to Z1 whole to the power n by n factorial, and this is what we have seen as Gibbs factor. Here we have a few questions. First one is the two particles and two states. We have to find the partition function. So first we have to find the partition function for first one particle. So one particle can be in 0 or E. So partition function is equal to e to the power minus beta into 0 plus e to the power minus beta into E. Now for how many particles are there? Two particles. So Z2 will be equal to Z1 whole to the power 2, and there is no description of the type of the particle, whether it is distinguishable or indistinguishable. Since MD statistics generally deals with distinguishable particles, we will go forward with the distinguishable one, that is equal to, the first one is 1 plus e to the power minus beta e whole to the power 2. Now here again there are two particles but three states this time. So z1 equal to e to the power minus beta into minus e plus e to the power minus beta into 0 plus e to the power minus beta into e. So z1 is equal to 1 plus e to the power minus beta e plus e to the power plus beta e minus beta e, and for two particles z2 can write z1 whole to the power 2. If the particle is mentioned is as indistinguishable, what we have to do, we have to divide by or multiply by 1 by n factorial, where n is the number of particles. So in both the cases we have to divide by 2 factorial or 1 by 2 if the particles are mentioned as indistinguishable, or in the question if it is mentioning about ideal gas molecules, you have to divide by 1 by n factorial or multiply by 1 by n factorial. Here we have the question: find the partition function for the quantum particles in Fermi-Dirac and Bose-Einstein statistics for the two particle system with energy levels 0 and E. If ZFD and ZBE are the partition function corresponding to Fermi-Dirac and Bose-Einstein distribution respectively, then which of the following is true? Here ZBE is given. You have to find the relation between the ZBE and ZFD. That is what the question says. Here's a question: find the partition function for the quantum particles in Fermi-Dirac and Bose-Einstein statistics for a two-particle system with energy levels 0 and E. The main sentence here is quantum particles which are indistinguishable. Okay, so let's start with Fermi-Dirac. We know if there are two particle system with energy levels 0 and E, we have this is E and this is 0. So in the first case I will place the first particle in A and the second particle here, correct? So there is no other possibilities, because interchange is not possible, together is not possible. So the system has energy, this is 1 into E and 1 into 0, so total energy is E, correct? So what is the partition function? Z is equal to e to the power minus beta E. Okay, now for Bose-Einstein statistics, same, the levels are 0 and E. The particles are A here and A here, that accounts for one set of energies. That is, total energy is E. Now both particle can be, since it is Bose-Einstein, togetherness is possible. That means the particle can stay together in both the states, same state. So both are in 0 energy, which means total energy is 0. Now the last case, both can be in the energy level with the energy E. Okay, so here we have 2E. Both of the particle are in E level, so 2 times E. So the partition function Z is equal to, let's start with 0, e to the power minus beta into 0 plus e to the power minus beta into E plus e to the power minus beta into 2E. So that is 1 plus e to the power minus beta E plus e to the power minus 2 beta E. So this is the partition function for Bose-Einstein, and here Z is equal to e to the power minus beta E, that is the partition function for Fermi-Dirac. Now here we have the ZFD, which is equal to e to the power minus beta E, and ZBE Bose-Einstein equal to 1 plus e to the power minus beta E plus e to the power minus 2 beta E. Now this is equal to e to the power minus beta into 0 plus e to the power minus beta into E plus e to the power minus beta into 2E. This we can write it as 0E. So 0E, E and 2E, 0, 1, 2. So this means ZFD whole to the power 0 plus ZFD whole to the power 1 plus ZFD whole to the power 2. So here, according to that option, option A is the correct answer. Maxwell-Boltzmann distribution, with we are going to find out how many microstates are present in Maxwell-Boltzmann distribution. Now WMB, this is represent the number of microstates, that's equal to n factorial by n1 factorial into n2 factorial into n3 factorial, etc. Now what are this n? This is n1, this is n2, n3, and it goes on. Now sum of ni equal to total number of particles, that is equal to n1 plus n2 plus n3, etc. So this is the number of microstates for Maxwell-Boltzmann distribution without degeneracy. Here we can write without degeneracy. Okay. Now coming to the Maxwell-Boltzmann distribution, the number of microstates WMB with degeneracy, you can write it as the same thing, n factorial by n1 factorial into n2 factorial into n3 factorial, etc., into G1, the degeneracy of the first state, to the power number of particles in the first state, into G2 into n2 into G3 into n3, etc. So this is the number of microstates with degeneracy for Maxwell-Boltzmann distribution. This is 3 different energy states, 3, and it goes on. Okay. Corresponding energies are E1, E2 and E3, and the degeneracy G1, G2, G3. That means this particular energy level E3 has G3 number of degeneracy. Now in this case 1, 2, 3, 4 degeneracies. Here 1, 2 and 3 degeneracies. Here 1, 2. Okay. In this case here there is no degeneracy. There is no splitting. Okay. So there is no degeneracy here. Here we will write once again, rewrite this microstates as uh, n factorial pi over I, which indicates the product, gi whole to the power ni divided by ni factorial. This is what is W Maxwell Boltzmann. This is very important formula. Coming to the Fermi-Dirac distribution, the number of microstates. Here these are 1, 2 and 3 different states, where n1 is the number of particles in state 1, n2 in state 3, and n2 in state 2 and n3 in state 3, and corresponding energies of the states are E1, E2 and E3, and on each state the corresponding degeneracy is G1, G2 and G3. Then the microstates, available microstates for Fermi-Dirac is equal to pi over I gi factorial into by ni factorial into gi minus ni into factorial. That is gi factorial divided by ni factorial into gi minus ni factorial, and this is can be also written as pi over I gi combination of ni, which is nothing but this one. Now there is a condition or validity of this statement or the equation, that is gi should be greater than or equal to ni, or gi divided by ni is greater than or equal to 1. Alright, or you can write ni by gi less than 1 or equal to. This is because since it is a Fermi-Dirac distribution, you have the condition for the state either ni equal to 0 or ni equal to 1. You cannot have more than one particle in a state. Coming to the Bose-Einstein distribution, we will find the microstates for this state. The number of states is 1, 2, 3 and it goes on. The energies are E1, E2 and E3. Corresponding number of particles in each state is N1, N2 and N3. And coming to the degeneracy, it is G1, G2 and G3 for each state. Then the W for Bose-Einstein is equal to Ni plus Gi minus 1 whole factorial divided by Ni factorial into Gi minus 1 factorial. So this is the number of microstates available for the Bose-Einstein statistics. Now here there is no restrictions. Gi by Ni can be greater or it greater than 1, or Gi divided by Ni can be less than 1, or Gi divided by Ni can be equal to 1. All these are possible because there is no restriction on number of particles.